Hello everyone. Thank you to Wendy and the editorial office for introducing the publishing um journals and the publisher. Yeah, so welcome everyone to today's webinar. So for today's webinar, we have two excellent speakers with us, and the title of the webinars is Advanced Additive Manufacturing Technologies for Inorganic as well as for Hybrid Materials. So before I move into the webinar for the first speaker today, an overview of MSAM, Material Science and Additive Manufacturing. Yeah, as mentioned previously, we are recently indexed in Web of Science under the Emerging Sources Citation Index as well as Scopus. So we're expected to receive our first impact factors as well as site score next year when they are released. Yeah, so we aim to publish articles quickly and rapidly, and of course, we accept good quality and high quality publications in the topic of material science in additive manufacturing. Yeah, so the editor-in-chief is Prof. Chua Chi Kai from Singapore University of Technology and Design, and I am acting as the associate editor for the journal. Yeah. So without further ado, I'd like to introduce our first speaker for today's webinar. He's Prof. Chen Zhangwei from Shenzhen University. Yeah, so Prof. Chen is a full professor and the director of Additive Manufacturing Institute at Shenzhen University in China. So his group is a very big group of 70 researchers focusing on various aspects regarding to 3D printing as well as its related topic. So he has also been listed as the world top 2% scientist from 2019 to 2023 in the Stanford University list. Um, Currently, he has published more than 140 high impact papers in top journals such as Progress in Material Science and Nano Energies as well, with more than 6,400 citations. So he is also a committee member of the additive manufacturing branch of the Chinese Mechanical Engineering Society. And finally, also a winner of the Guangdong Provisional Natural Science Second Award, and among many awards that he have won. Without further ado, let us welcome Prof. Chen for his today's talk on 3D printing of inorganic materials.
All right, thank you very much for processing. Nice introduction. I'm glad that I've been invited for this seminar. And so I share my screen now. I think you
Yes, please.
stop your sharing, and I stop my sharing.
Yeah.
Okay. Thank you.
Yeah, let me stop share.
Yes.
Uh,
So can you see my screen?
Wait. Oh no, it's still on my screen. Let me see. Let me stop
Yeah, we
share
can see
now.
your screen.
Oh yes. Yeah, we can see your screen now actually.
So now
Yeah.
this is my screen. Okay. Is
Yeah.
it? All right. So
Yes.
I can start my talk now, right?
Yes. Please go ahead.
Thank you. Thank you very much. So my topic today is additive manufacturing of inorganic materials. Basically, it's ceramic-based materials for advanced application. So my name is Zhang Weichen from Additive Manufacturing Institute in Shenzhen University in China, and currently I'm a professor and director of this institute. And so these are the table of contents I'm going to introduce because the time is limited, so I'm not going to talk too much about the details of some of the aspects and more roughly, give an idea about 3D printing and organic materials, basically mainly for ceramic materials. And a very brief introduction to the group. So our institute, we have about 50 master students, including also 7 PhD students. And we have 6 faculty members as well. So in total, we have almost 70 people in the team for research, mainly focusing on 3D printing including the material side, also printing technologies, and then the characterization of the printed parts, and then the application side. So the material involved, we have polymer ceramics, because I'm working on ceramics, and there are also the professors working on metallic 3D printing, which is a hot topic as well. And we have a range of 3D printing facilities in our institute. And the application side, we are mainly working on energy sectors, as well as the structural or functional components we're producing. And this is a group member photo 2 years ago. So we have also some other students and faculty members or postdocs from other countries. So these are the machines we have in our institute. For example, the DRP 3D machines for ceramics, for resin, and also the DIW direct writing machine, SRAM machine, inkjet printing machine, and these are the printing machine. And we do have some sort of, because if you are working on 3D printing of ceramics, we have to make our own slurry, or paste, or suspensions. It depends on the viscosity you use for the material. So we prepare our suspensions or slurries using milling, and try with the particle size distribution, and sinter our final printed components using furnaces. And we also got some other characterization facilities, for example, the microscope and mechanical testing machine. So basically, for over like 80% of the work we can do in our institute. An introduction to the 3D printing of inorganic material, basically for the ceramic part, as the forecast predicts the in like 4 years time, then we have like 7 times the increase regarding the high-end hardware, and also the technical parts, material side as well. So the ceramic or inorganic material additive manufacturing, the market is still expanding. For ceramic 3D printing or inorganic material 3D printing is not like the resin or metallic components, because if you try with the resin or polymer, metallic 3D printing is mostly like one step, although there are some heat treatment or other type of step, post-processing process involved. They are straightforward. So for inorganic or the ceramic additive manufacturing, you have to prepare your own slurry, which contains lots of polymer contents. We have to remove them afterwards, after the printing process. So the shaping is basically directly relevant to the 3D printing process. Then there's heating. If the material they are aqueous based material, then we have drying as well. So the heating, drying, they are some sort of a basic process, post-processing for the 3D printing of ceramic or inorganic material. So we were honored to have this publication in 2019, and the title is 3D Printing of Ceramics, a review, and they got nearly like 2,000 citation till now. We classified over 10 types of 3D printing technologies that can be used for printing ceramic, the inorganic components. So basically, you can see from this table, in terms of popularity, the stereolithography or DLP, digital light processing. These two processes are considered as the most commonly used 3D printing process, or we say now today is VAT photopolymerization (VPP). And there are also like binder jetting and selective laser sintering, which are of course, very useful for 3D printing of ceramics, inorganic material, and the very low cost one is the direct ink writing, because it's just like squeezing material from the nozzle, extrusion based principle. And these are some of the examples which are quite popular in the industrial or the academic field for research purpose. And some of the results like I'm showing here are the 3D printing, 3D printed ceramic components. I was holding all these pieces of materials, components, because I want to show that these components are very delicate and also fine feature with high precision. So these samples as well, the outer circles, they are mostly like oxide materials, and the inner circle, they are some sort of a polymer ceramics or inorganic material, which are more, in terms of functionality, also the structural durability, much higher quality. So they have different colors, which are very, very different from the oxide materials. And these from now on, I'm going to show you some of the examples in our group we prepared for the inorganic material 3D printing. So the first one is cauterized ceramics by photopolymerization 3D printing, and the basic background is the purification of air for the vehicles, because nowadays in China you can see that we have lots of electric vehicles, but previously, like dated back to 5 years ago, the majority of the cars are using gasoline. So the in terms of pollutions, in terms of purifications, large demand. So at that time, we started using cauterized for 3D printing, but people try with different kinds of 3D print technology. For example, SRAM, DRW, they have low resolution. So at the time, we proposed using the 3D printing, like photopolymerization based 3D printing method for preparation of this kind of honeycomb structure for purification purpose. And we start using our prepare our own slurry. The slurry is based on the commercially available the powder, different particle size powder, and then we try with adding lots of additives, organic additives for example, the surfactants and dispersants. These kind of additives can help the improvement of the rheological properties of the slurries we use. And after preparing the slurries, we test the sedimentation ratio as well as the viscosity, because these two factors are very important for maintaining a stable slurry. If the slurry is not stable, for example, if you print using printing during the printing process, like 2 or 3 hours or even 10 hours past, then the slurry sediments. So that can become a problem, because if they are not stable, all right. So we try with different kind of recipes and see that which one is the most stable one. And afterwards, we try with the stable one, most stable one, and see how we can print well with this kind of stable slurries. So we try with different units, for example, the holes, the single lines, the single layers, and lots of things we can do, and test the curing thickness as well as penetration depths and the critical exposure energy and so on. Lots of things we can do for characterizing the printability. So this is a special term when it comes to the 3D printing domain. The printability is a vital factor that control the printing of the final 3D parts. Yeah. Based on the designing and also the topological improvement or the optimization, then we have been able to design different kinds of structures, which are very, very different from the conventional parts. And for example, here I'm showing if we can see that the velocity here are much, much higher than somewhere surrounding this area, then we can put more channels, put more porous structures here. So these are not the same as previous design using conventional methods. Then after printing, we do the test. Okay, some of the research are still ongoing. Then we are able to print many sorts of inhomogeneous structures, which are not possible with the conventional technology. The second one is lithium oxosilicate, which is very interesting using 3D printing, wet photopolymerization 3D printing. So the basic background is, nowadays we have many nuclear plants. Nuclear plants are based on fission, but there are some sort of pollution, some sort of leaking problem like in Japan. So the fusion, another alternative method, fusion, nuclear fusion, which is the ultimate energy resources for humankind. So it is regarded as a man-made sun. Okay, in the sun, there are fusion. So this is a nuclear fusion happening, and currently it's still ongoing because it is not yet commercialized. So what's happening inside? Because currently the fusion is made by the isotope of hydrogen, the tritium and deuterium. And the deuterium is abundant from the nature, like the sea water, and the tritium is non-existent in the nature. So we have to produce the tritium by breeding. The breeding means that there's sort of a reaction, the generation of tritium by the lithium-based material with the I think it is like a hydrogen isotope. So conventionally, there's a stack of pebbles become a pebble bed. Inside this pebble bed, there's a flux of gas to react with lithium-based material. And this kind of configuration, I mean, the bed configuration is not good enough because there are two main issues. First one is the purple bed, they can contact each other with point contact. So at high temperature, there will be a sort of stress concentration. So this is not beneficial to the long-term durability. And the second issue is the stacking of the purple will be there was there were some sort of a geometric limit, for example, like 70% of packing density, and we cannot go even higher. So these will limit the tritium breeding efficiency. And based on this observation, so we try with using lithium oxosilicate material, then using 3D printing to change the configuration, and we start prepare our own for the first time our own slurries because the lithium oxosilicate is a very reactive material. It can react with the CO2 and HO2 in air. So we have to put all these material processing procedures inside the inner atmosphere, like blood box, and then we produce our own slurries. It's similar to previous case. Then we use photopolymerization 3D printing to print the such kind of configuration, the structures which is no longer the purple bed structure, and we have a lattice structure here, and we test some of the results, and they are much better than conventional purple bed structures. And second thing is we propose a generative shaping and material forming in Chinese 创新创才, this kind of strategy, because the lithium oxosilicate, the material itself is very expensive. It's we can say that it's not commercially available because we have to get this kind of material, the powder, from our collaborator. So there's no existence in commercial market. Then expensive, okay, the first thing, and secondly, it's sensitive to air. And these two issues are not easy to tackle. So we try with combination of A plus B, means that there's two inorganic material. So this one and silicon dioxide, these two material, they have no longer. I mean, the firstly is cost effective, low cost, economically, and secondly, they are no longer sensitive to air, and because they are cheap and not sensitive to air, so we can mix them together to become a mixed slurry, then do the 3D printing. So the 3D printing in this process is making the shape. Okay, so there's like a generation of the shape. Secondly, at high temperature, these two materials react together. It's like reaction sintering. Then we have a generation of new material. That's the target material, lithium oxosilicate. All right. So low cost, abundant resources, the simple processing. This will make, overcome the two issues I previously reported. And there are also, of course, for 3D printing, there's varied the packing density starting from 45 to 80%, even higher, we can go like 90%. So there's a flexible design and of course the gradient structures we prepared for using 3D printing. And secondly, we try with inorganic organic combinations. So previously we have on the left hand side, there's two inorganic material together, A plus B, and with generation of C. And now A plus B is inorganic and organic. Okay, so this is more chemical or the material side. We prepare our own material slurry, then we try with 3D printing to get the shape. And then at high temperature, like after sintering, there generation of new material, targeted material. All right, so this is so-called generative shaping and material forming process. And we try with this material and it works very nicely. And now we're trying to expand the applicability in other material as well. And these are some of the results we're showing here. They have a very good mechanical properties as well. And also during the whole process, you can see that we have some sort of improvement because you know that 3D printing can generate sort of a staircase effect. There's no way that we can eliminate it without any sort of chemistry principle behind. If you only try with minimizing the layer thickness, there's always existence of staircase effect. But using this strategy, we can just reduce the staircase effect, like enhancing the surface quality. For example, the staircase effect can be largely reduced, and surface roughtening reduced like over 70% compared with the conventional method or previously reported 3D printing method. And we are trying currently working on the reaction principle and see how it changed these surface roughness. Of course, there are some basic evident principle, like there's liquid freeze coverage during the high temperature sintering. Then we are still working on that and see how it can improve the final results. And of course, we try with the dual phase components like lithium oxosilicate as well as lithium titanium, these two components, and see what can happen for 1+1 over like this is larger than 2 because of the multi material. Then we can have a lot reaching higher relative density as well as smaller grain size and better crush load. So the crush load is very useful for the chitin breeding application. And this is a whole process. And our student also drew this very nice picture showing that compared to the conventionally like arbitrary bulk porous material bulk porous structures, then the purple bed may have some improved performance. If we try with 3D printing for the lattice structure, then the performance can be even better. And then if we try with the GMS, generative shaping and material forming strategy, the final result is much better. So we try with this material, and then we are going to expand the applicability of this kind of strategy and see how it can change other combination of materials rather than lithium-based material. Okay, so afterwards we have some sort of national media coverage reporting this kind of outcome, including the English medias as well. And the next one is silicon carbide ceramics by photopolymerization. So for silicon carbide material, which if you want to use red photopolymerization, is much difficult than the oxide material, because for the silicon carbide there's a large absorption coefficient of light compared to like alumina and zirconia, like 10 times even higher. So it's hard for them to be photopolymerizable. And what we propose a kind of pre-oxidation. It means that for heating in air or even in like oxygen atmosphere, then there's a formation of very, very tiny thin layers of silicon dioxide, coating. So these kind of shell coating structures can just improve the printability. Then you can see from the left hand side the single layer thickness can be improved like 3 times. So it's now like 107 micron, and the original one is 40 micron, so it's 3 times. And now we have like 120. So afterwards, based on this strategy, we can successfully produce a 3D printed silicon carbide material with highly complex structures. And you can see that the whole strategy very, very smoothly we can apply for different kinds of structures. And you can see that after printing, after sintering, the structure is very delicate and very refined structures we can obtain. And the next one is photopolymerization for the polymer-derived ceramics, PDC. PDC is not a new material, but it is new. It is new material for 3D printing. Okay, so people in the US, they have published this paper in 2015 using stereolithography to produce the PDC material, PDC structure. So you can see that in the image C, then there's pre-ceramic polymer. So there's a very, very different, distinct feature for PDC 3D printing, because there's no involvement of particles. It means that there's no slurries, no, the sedimentation, no viscosity issues, lots of things can be avoided. So using ordinary printers, like very cheap printers, you can just print the PDC, and there's no scraper needed for leveling the high viscosity, the slurries like previously reported for all sorts of powder-based slurry. And the resin, of course, is cheap, and we one more thing is we can have a very fine control over the molecular level. Then we can dope lots of like titanium, zirconium, like ferrite. So all sorts of materials we can dump inside this molecular level. Then the process, because the doping or the controllable recipe can be very advantage, because some sort of enhanced features, enhanced performance like mechanical properties, and also the electromagnetic performance can be enhanced by this kind of strategy. And of course, resin. Okay, so the only additional step is using the high temperature pyrolysis. Well, it's the same as sintering, but the temperature is slightly lower. We call it pyrolysis because the whole process is like a more chemical reaction compared to the normal sintering stage. And we produce our own recipes. This is more chemistry, and we try to see the viscosity, the depth of penetration, and also curing behaviors, all sorts of things. And then we measure the sintering or the pyrolysis performance as well. And finally, we can produce very good, refined features using this method. Of course, you can see from this slide, then our aim was to produce a high strength and low density structures. It means that for the high strength, there's enhancement of the mechanical strength, and secondly, the low density, it means specific density is getting lower because we try with the design of lattice structure. So low density and high strength very useful for the outer space applications because these material is called SiOC, silicon oxide carbide, which can be very useful for the sharding of electromagnetic waves in aerospace applications. Of course, try to use this method to produce a 3D printed PDC is very, very difficult sometimes for larger scale, larger size samples. So we try with the investigation of how we can improve the thickness, how we can improve the crackings happening inside these structures. Because you know that for this material, there's no powder involved. So that weight loss is very, very high compared to the powder-based slurry, and almost like 80% of the weight can be removed from the structure. So there's a large shrinkage as well as the result of crackings and deformation. And we try with lower melting temperature polymers, which can be used inside this material, create microchannels, which can facilitate the removal of the high melting temperature polymers or additives organic material, and this will make the channel smooth for the removal. And as a result, of course, the cracking can be eliminated. Then we try with the different thickness also for the monolithic material as well, and these have a larger size as well as good mechanical properties. And we published paper in review paper in Progressive Material Science regarding additive manufacturing of polymer-derived ceramics. And on the right-hand side, the journal Inorganic Material, I designed this cover piece because you can see that it is interesting. Starting from the ultraviolet light, then exposed onto the resin, liquid resin, pre-ceramic resin, then we can create a lattice structure, PDC, by, of course, the high temperature pyrolysis. Afterwards, the background is aerospace background. So it's interesting that the whole procedure can be demonstrated here. And have some very minor summary for I have been talking about previously. So starting from the inorganic material like ceramic powder, which is target powder from the beginning to the end. So it's just the generative shaping by 3D printing. So it means that the 3D printing is only to create a shape. There's no possibility of generating new material. At least the majority of material stay the same. Then we propose using A plus B methods or the generative shaping and material forming method, like combination of inorganic material, A plus B, inorganic material, and there's inorganic material with organic material. And finally, have the precursor method using PDC. It's all organic material. So this is the generative shaping and material. And we also produce our high-speed VPP 3D printing. You can see that it's like click, okay, with the underlying mechanism is the photo inhibition strategy. Then we want to use this kind of method to produce the, of course, firstly, the commercially available resin, and secondly, the PDC precursors. And then we try with the slurries, of course, because the slurry is very difficult with high viscosity, and the viscosity increase with the resin, PDC precursors, and then the slurry. So with the increase of viscosity, the difficulty of also augmented for this kind of technology. Well, there are some benefits, of course. First one is the elimination of staircase effect using this strategy, and secondly, of course, the improvement of isotropic behavior, which is very useful for nowadays. For 3D printing, XY direction is different from Z direction if we try to do the mechanical testing. Then, apart from the VPP, photopolymerization, we also work on the solid oxide fuel cell using inkjet printing because time is limited. So I only briefly introduced that using 3D printing can produce like inorganic material within the SOFC components, like electrode, electrolyte, because some of them are dense, some of them are porous material, and prepare our own inks with low viscosity and high solid content, and we were able to produce the porous structure and very thin electrolyte structure as well, like only 4 micron with 20 passes, 20 layers, and then we try full battery as well to see how it can improve the electrochemistry behavior. Okay, so I'm not going too much on these conclusions. I think my time is over, and thank you very much for listening. And if you have any question, I'm glad to take it.
Yeah,
Thank you.
thank you, Prof. Chen, for the very insightful talk on 3D printing for inorganic material. If there's any questions from the audience, feel free to use the chat box or you can unmute yourself. Yeah. So we welcome any questions from the audience now. Yeah, maybe I will start the ball rolling. Yeah, Prof. Chen, you have shared quite a few 3D printing techniques and your work on very interesting ceramic material system. So, in your view, right, do you think that development of the process is more important, or should we look into using existing processes for new ceramic material?
Thank you for asking the question, Professor Shin. So, you mean that the existing technology and the comparison with the novel technology? I'm not quite get your question. So you are asking, can you repeat it, please?
Yeah. Yeah, I'm trying to find out because you are using I guess new existing 3D printing techniques to create series for to process series for ceramic printing. So it's more towards the work on material development for the techniques, right? So do you foresee in the future there will be new techniques that is specifically catered for ceramic material?
Yeah, that's an interesting question. I mean, in some of the slides, I have been mentioned that actually for 3D printing of ceramics
Mhm.
I mean the history of 3D printing ceramics is shorter than polymer and metallic components because it's
Mhm.
even more difficult because of the high high hardness for mechanical properties. So they are very, very difficult for 3D printing. And most of the currently existing 3D printing technology used for 3D printing of ceramics, they are some sort of, from the basic, very previously reported 3D printing technologies using
Mhm.
polymer and metallic components like SRM, SRS, and also photopolymerization Okay, photopolymerization only previously the very first one by Charles Howe developed like stereolithography only for polymers, only for resin. And then if we add some of the powders inside, that we do 3D printing for ceramics. But of course, we can make some of the new development of the facility, the machines for ceramic only. I mean, I think DIW is a good process to start with, and it's low cost, and also it's much more versatile than the other types of 3D printing technology. There should be some solution with other type of technologies. We can just combine them together and to get a new feature. I mean, there are lots of development already in the domain to develop new technology for 3D printing of ceramics as well. But I'm very much looking forward to the new technologies, and we can use them with high efficiency as well as high resolution. I mean, the resolution is always a headache, okay, for 3D printing for any kinds of materials. All right, my answer.
Yeah.
Thank you.
Yeah, thank you, Prof. Chen. We have one question from the audience. Yeah, he would like to find out what are some of the applications of this 3D printed ceramics.
Yeah. I mean, I have showed some examples. For example, like lithium oxosilicate, we can use it in nuclear fusion, which is part of the tritium breeding unit, and it can produce the tritium to react with the deuterium, which is abundant in nature. Then there's an outcome of the high energy, which can be used the energy sector. Of course, for other energy like lithium-ion battery and solid oxide fuel cells, they are all applications you can make for 3D printing. And I mean, for the general rule, when I look into one application which can be applied with 3D printing, I'm really interested in the new features, geometric features, for example, the highly complex structures, because conventionally you cannot use like conventional method to produce highly complex structures. Then 3D printing enables the realization of such kind of highly complex structures. So this is the most, I mean, influential 3D printing to be applicable in different domains.
Yeah,
Thank
thank you,
you.
Prof. Chen. I think we have a question from the audience. Yeah,
Thank you very much.
you can unmute yourself.
Hi,
Yes.
Professor Chen. Very nice talk. I'm Li Feng from Sydney, Australia. So I have one question regarding the photopolymer printing. Just now you mentioned that one of the advancement of this kind of photopolymer printing is trying to get ceramics to be mixed with the photopolymers. Then you do the like a photocurable type of printing. Can you elaborate a little bit more? How does it work? Is it like just when you polymerize the polymers, then the ceramics being trapped within the structure, or is there any chemical reaction between the ceramics and the photopolymers?
Yeah, thank you very much for your very nice question. Yeah, it's some of the underlying principles for 3D printing ceramics using photopolymerization, and I would like to say that actually the especially for wet photopolymerization, the photopolymer, because after 3D printing, they like cross-linking of photopolymers. So cross-linked network can just wrap these or enclose these ceramic powders dispersed in this resin. It means that the wrapping or enclosure of the powders can make the 3D features reliable. Okay, it can be 3D objects. I mean, binding, at high temperature is just to remove the photopolymers. So photopolymers is kind of media, because finally at the end of the day, we only use powder. There's no photopolymer inside the ceramic body after high temperature sintering. So the photopolymer only a tool or media to hold the particles. And during the high temperature sintering, as the temperature increases, then the photopolymers or other kind of organic materials, they can be evaporated, because of the temperature. And there are two steps. First step, the evaporation at lower temperature, like below 700 or 500 degrees C, then the evaporation of the photopolymer creates the vacuum. Okay, create the porosity, and at that time there's no sort of very very delicate, very very soft of the powders. So at that time it's called debinding. Debinding time, during debinding, after debinding, the strength is very low. You cannot even handle with your manually handle these structures. But at even higher temperature is called sintering, and at that stage there's a so-called necking. The sintering necking, powders become connected together, and they are cozoning and densification. Cozoning means that the powder can be combined together. I mean, two powders becoming one powder. We are just encompasses each other and become one powder. And there's densification means that the porosity can be eliminated at even higher temperature. So at that time there will be shrinkage. So the shrinkage never happening in the binding process, but at higher temperature. Defects like the crackings. Of course, this is the very very phenomenal factor in the printing or sintering of the ceramics. The crackings can be generated in sintering process. That's all about the printing, binding, and sintering. But finally, I mean, at the end of the day, we only get the ceramic powder. There's no existence in the ceramic side, sorry, the ceramic components, any components of photopolymer. There's zero photopolymer in the final ceramic components. Yeah, I think
Yeah.
I can. That's
that's
the thing I can say. Okay, thank you very much.
Process, right? It's just like a post-processing. So you put this printed object, then put in the stove to the oven, then raise the temperature to a certain degree, right? That's the sintering process to finally to connect all the small powders to make a subject.
Yeah, that's exactly the same as you said. So at high temperature, maybe for different oxide material, different even like silicon carbide, silicon nitride, even going higher, like 2,000 degrees C. Yeah, that's after the high temperature sintering. So then we can get the densification, cozoning of the material or the powder grains, so that finally we can have a highly dense, like I'm not saying 100% of density, but at least like 98% of the relative density we can get. So based on this higher density means that higher relative density, lower porosity, and higher mechanical strength. So that's all about ceramic sintering.
Thank you. Yeah, that's very interesting. This is a very interesting technique. Yeah, the first time I heard. Thank you so much.
Thank you.
Yeah.
Thank you.
Yeah, thank you, Prof. Chen. Yeah, so we are going to move on to our second talk for today. Yeah, let me introduce our next speaker. Uh, yeah.
I think it's still loading.
Okay. Let me try to share it again. Okay, let me try it again. Okay, sorry about that.
Hi, Dr. Mika, can you hear us? Hello? I think maybe we
I can
got
hear you.
network issue. If you like to share the screen, you can just share your slides here.
Let me, right.
Maybe Professor Singh could stop the set sharing. Yeah, it works now. Yeah, we can see your
So you're
slide.
able to see?
Yeah, cool.
Yeah, sorry about that. Perhaps I will still let me introduce the speaker. Yeah. Yeah, so our next speaker with us for today is Dr. Mika Salmi. Uh, Engineering at Aalto University in Finland. Yeah, he's a distinguished young scientist with recent research focused on the emerging field of 4D printing, which is a very exciting field, definitely. He's also listed in the World Top 2% Scientists by Stanford University and has published more than 80 peer-reviewed papers, with two of his most cited articles surpassing 400 citations. So he's also an editorial board member of our journal, Material Science in Additive Manufacturing, and an editor for Progress in Additive Manufacturing. So today he will talk to us regarding 4D printing of hybrid materials using desktop printer. Yeah, so without further ado, let's us welcome Dr. Mika.
Thank you, and
Thank you.
thanks for the opportunity to have this presentation. So I will tell a little bit about the desktop printers, but first I would like to say why desktop printers. So if we think about like expand or widening the research, so the more easier to others is to to continue or develop from there, the more influence it might have. So that's why this research we are looking at the desktop printers with the hybrid material and 4D printing approaches for that. So I come from Finland, so which is north part of Europe, and basically this is our campus. So we are next to the sea, but we are only 30 minutes from the capital city of Finland, from Helsinki by metro. And we have a student village, and we are like a really campus-based university. So all our actions are in the same place. A little bit about the Finland. So we have. It is normal to have the temperature between -30 to summer. It might be quite warm, and we might have a snow and quite a lot of snow even at some point. So now to the additive manufacturing research at Aalto. So we have actually done that since 92. So the first commercial machine was sold in the 89. So quite from the beginning. And we have about 15 to 30 researchers. It depends who you count. Do you count those who are doing other things also than AM, but are related to maybe the AM? But about that, and so I have been about 15 years in this field, and I still feel myself as junior here. So, and we have all ISO, ASTM standard defines the different process class. So we have from all of those classes, we have devices in-house, more than 30 or even 40 different kind of printers. But basically what we do, so basically we look that you should have some kind of meaning. So you should have some kind of application. So maybe it's some kind of new products or service based on the additive manufacturing. We have done a lot of in the medical applications. Spare parts and digital spare parts has been one big one. 3D printing optics or smart parts, key performance components. And then it's very easily to go, so what's the material and what's the quality there. And maybe we want to maybe process some new materials with the AM technology, as shown in the previous presentation. Also material modeling, especially for the metals, is in our interest. And then you need the AM technology, so we develop our own technology and we combine is very important, 4D printing, AI, especially the process monitoring related things. And then for the printing, you always need the 3D models of the design is where you can optimize and have the better performance. So this is what we do in Aalto. And then to this 4D printing. So basically what's the 4D printing is, so you 3D print the object. So you expose it to stimuli, which can be temperature, light, or something else. And then with some time, it will change it form. And that is how it's defined. And the fourth dimension here is the time. And then if you try to define what is a hybrid material, so in this presentation, I will use it as when we are combining of different material types. So we have metals that we combine, for example, with the plastics, or we have metals that we combine with ceramics or so on. So that is a hybrid material, not combining two different steels together or also multi-material with the powder bed fusion, or then there is this hybrid material parts where there is a safe memory polymer and then there is a carbon fiber inside of that. Okay, now more to the research what we have done. So first one is like a self-sensing hybrid parts. So use the copper. So how we are using an anisoprint. So this is a material extrusion type of printer, but what's unique here that it can feed fibers through nozzle, and we can position fibers in the inside of the prints. And of course, we have tuned the device and adjust it so we can put also example metal wires inside of the device and position metal wires inside of a plastic parts. So what was the first what we tried with this? So trying to make this kind of like a self-sensing parts. So basically, if you know how strain gauge will work, so you have a strain, and then you have this kind of like gauge, and then there is like you're measuring basically the resistance between there, and then if you are bending that or pulling or even pushing that, you should have a different resistance because there is because the material or the diameter of the wires will slightly change. So what we did and what we studied, so we make this kind of two different kind of test plates from a different materials, and then we try to bend them and then see how well this resistance will change. So different kind of specimens. So specimen A, so we have only one wire there. So we have a flat plate with the width of 35 and a length of 70 millimeter, and only one carbon fiber or one copper wire there. And then we of course try to use the whole width of the specimen back and forth or basically it's a one wire, but going back and forth as much as possible. So 33 times going back and forth. So try to make the phenomena more, so the resistance change would be bigger because there is more lines there. So this is how we test it. So when we make a jig where we are going to push it, and then we are measuring how much we are pushing, and we are measuring the resistance change, and this is the results. And actually, you can quite well predict how much it's been bent if you have enough fibers there. So if we first look this picture from the bottom, from the left in the bottom. So this is a specimen A with the carbon fiber. So only one wire of carbon fiber, and here you can actually see that from here it's hard to say anything because there is so much of noise in here. So only one wire, and you cannot predict too much. But then if you have there only one copper wire, this follows quite nicely this how much you have deflected and what's the resistance change there. And then of course, if you want to have it better, adding actually even help, because there are these corners, and also you don't even get too much better values, slightly better, but not too much. And then with the carbon fiber, so there where you add the carbon fibers, you can get that better because this noise will get lower. So basically about this, so this self is better than carbon fiber, and what would be maybe the next steps would be to have a more accurate and stable resistance meter, or maybe some software to remove the noise there, and maybe building a Wheatstone bridge so that could turn this resistance to voltage and have a better accuracy there for the measurements. But basic concept work. Okay, the next one, this is hybrid parts with shape memory polymer and carbon fiber. So again, the same printer, but now we have a 4D printing filament there, actually from Shenzhen, China, and then we have a carbon fiber from the anisotropic print. And what we are looking here, we are trying to look if we are outer geometry of the specimens would be the same, but how this different kind of layouts for the carbon fibers. So we have a horizontal layout, we have a vertical layout, and then we have a cross layout. And how the samples, so first we make a bottom layer, which it's a pure shape memory polymer. Then we have layers where there's carbon fibers and the shape memory polymers, and then we have the top layers which are like again pure shape memory polymers, and between the fiber layers there is also shape memory polymer. So then we can get the nice matrix parts. So the process, so we test the specimens, then we are heating up them at the 80 degrees Celsius for 10 seconds, and then we are having this kind of mechanical wise. So that is we want to change the shape. So when it's in the soft state as 80 degrees, we will change the shape and let it then cool down. So then it will have that shape from this wise. So it is around it slightly, but not too much so that something will really start breaking there, and then we don't know actually what we are measuring. And then we dried those samples, and then we recorded or put those in hot water and recorded the shape recovery process. So using digital camera and camera monitoring and some software with that to really get some detailed answers how these different fibers would influence there. So here are the specimens. So we have a control specimens, so no carbon fiber, vertical carbon fiber specimens, horizontal, cross with the layout 40, cross with the layout 50, and cross with the layout 30. So different kind of infills, and of course we could use their different kind of fill outs, but this was the first to try to see. And actually there is a quite big difference between these. So actually those fibers will work there as like a spring. So you can have a better recovery rate with this. You can have a like a better fixity with this. And here are like some results. So if you look the here, so the yellow line is the control. Actually, we can influence that how fast and how much it will recover. So example of shake recovery with that geometry, it's about 80% with the control. And you know, if you put the vertical, we can get where, or having the cross, we can get somewhere in the 90%, so which is much better. But of course, if you want to have it worse, we can put the horizontal. So with the fibers. And here is an example. So we have a horizontally versus vertically. So the horizontal is faster, but this recovery rate is not so good. Keep the shape after this forming, not use the hot water yet, but after this wasting. So that's better in the horizontal one. And then in the vertically, that's a slower, but I have a better recovery rate, and fixity is not don't like collapse there. So actually influencing the properties and what makes this is interesting, because we can put different layouts in the different places. So actually we can really try to tune the material how it behaves. So some conclusions. So improve the shape memory capability to have a higher shape recovery ratio or higher shape fixity ratio. And this fiber layout and density has a big influence. And to be honest, more fiber is not actually better. So what is optimal is still under work and to find out. Okay, then we could go to the next one. So this is again, we have a desktop printing. So we have a material extrusion, but now we take another process after it. So we are using atomic layer deposition to have there's some kind of electrical conductivity. So what we are aiming here, so we are aiming making an electric circuit for ultraviolet light sensor. So this is a space application related thing. And we have a standard like Ultimaker Pro as S5 Pro printer, and we are combining ABS and polypropylene. So actually the first thing in here was to find suitable materials that we can join together in a not in a that having a huge mechanical properties, but having this kind of that we can print them together. And the other one should be where this ALD process stick very well, and the other one where the ALD process don't stick at all. So we tested actually plenty of different materials to try to see which could work in this ALD process, and then we figured out, okay, ABS that will work very well in the ALD process, and coatings don't attach there. So very good material pair for this kind of selective coating. And then we use the aluminum oxides in the ALD process for the first. And the problem there is that we cannot go too much over the 100 degrees, because then the shapes start like forming and it don't work. And many ALD processes require higher temperatures. So that was one challenge. But there is processes which use only 100 100 Celsius for the coppers. Those are like a water. And that was like a combination of different knowledges. And then we actually tested this. So we had the normal one. We joined the components in the circuit, and then we put it as a test. And actually this, if you look the baseline sensor and then this 3D printed sensor, it actually quite nicely follows the curve. Of course, there is some voltage difference, but if you know what's the voltage difference, because it seems quite constant here, there is no huge difference there. So that's actually quite good. So we were able to 3D print this sensor board for this ultra wet light sensor, and then this was selectively conducted. So we were able to do it. So that would, in the end, mean much more automatic process. So if we could print the parts and then we put them in the ALD reactor, and then we can get out of the circuits ready. So, and there was some additional resistance in the 3D printed sensor, but that wasn't very significant. Okay, then we could go continuous carbon fiber with reinforced bronze or continuous carbon fiber reinforced bronze matrix composites. And for this, we are again using a material extrusion printer, and we are using again carbon fibers there. But now our filament is containing this kind of bronze. So it's containing metal particles, a lot of metal particles, and we can sinter them in our oven, and then we can have a metal parts out from the basically desktop printing with the material extrusion. But unique here that we want to really put carbon fibers there, and we know that the carbon fibers will survive in those temperatures. What we are using the sintering. Of course, what sintering thing here is that actually a lot of those properties are made during the sintering phase. So what we use sintering here, we go from 2 degrees per minute from room temperature up to 300. Then we use one slightly slower when something starts happening. So only 1 degree per minute up to 450, and then actually when this binder from the filament will start like burning away, and held it for 1 hour, and then go slightly faster to the 900 degrees and held there 5 hours, which was the target sintering temperature, and then cool down. But again, quite similar as this with the shape memory polymers. So we made the test parts, and we put there different kind of like fibers there. So if you want to optimize some properties, so example for bending test, we put this kind of cross pattern with the infill of 50% there, and then for the tensile test, we put the like a line pattern with which is like a parallel to the tension direction and infill of the 80%. And again, we need to put like we cannot put the fibers in the top of each other layer. We need to make non-fiber layers there because they are slightly thicker than the normal layer. So we need there to put layers with the fibers, so that otherwise the printer don't work. Here is some testing and results. So we made the 3-point bending test, and then we made the parts without the fibers and with the fibers, and compared what we can have there, and that will affect like different kind of properties, and what we can give there better. Okay, flexural strength would be maybe slower. But others, the yield stress or ultimate tensile strength, those where we can improve or change the tensile modulus. and having like a better properties with the fiber addition. And again, this is like a first test and to see what we can do. But again, this allows that we can try to define the parts or put the fibers in a way that the parts would have a better properties where needed. So that's the idea. So some sort of conclusions. So this continuous carbon fiber bronze composites with the material extrusion. There is some issues of forming gaps between this CCF and then the matrix. And I think that will slightly lower the conductivity at this point. So there is actually a lot of more research needed around this to see how and what we can really achieve with this. And some overall conclusions. So there is something coming where there's a sort of sneak peek video. So all of those concepts work. So, but still need a lot of more concrete applications or tuning, or trying to do what's the application. So we will try to paint the processes slightly here, and of course looking the parameters, how the geometry should be compensated, different materials. Sintering is a very big thing if it's there. I think it's same in the ceramics. And then some combination of these that's still bending, and something more complex is under work. So thank you. That was the short presentation. Questions, comments?
Thank you, Dr. Mika, for the intriguing talk on 4D printing, especially using our desktop printer. So again, we welcome questions from the audience. If you have any questions, feel free to use the chat box, or you can raise your hand and unmute yourself. Maybe allow me to ask the first question again. So for 4D printing, right, there are a lot of exciting research ongoing using 4D printing for wearables devices or even robotic gripper, but not that much real or in actual applications in the industry. So perhaps you can share your thoughts on what are some of the hurdles or barriers for the industry to pick up.
That's a very good question, and you're right that at the moment there is not so much business around the 4D printing yet. I still think, but I think it is like if you think any other manufacturing processes, so more complex parts or more complex properties you can make, then you can replace some parts with the like slightly more complex parts, which can have a same function as the previous one, which was maybe some kind of assembly of different parts with different properties. And so I think we will see. I think robotics is one where we definitely, and I think some companies are even trying to make some grippers and those with the, but of course it's also about the stimuli, and is it like a one-way shape change, or is it a two-way? In medical field there is also a lot of potential, but of course there the approval processes can be quite long before they are actually in the use. But I think it will soon start having different kind of commercial applications and values. But of course that requires the basic research. So we need to increase the TRL levels there. So then we are like more ready, and of course industry want the proof. They will ask, oh, how many will this be, million cycles, or how many cycles this go back and forth, and maybe you are not there yet. So the quality is one thing also.
Yeah, thank you, Dr. Mika, for the very good answer to this question. Is there any further comments or questions from the audience? If not, thank you again, Dr. Mika. So
Sure.
maybe Let me try to share my screen again before we close the sessions. Let's see.
Let's
Yeah.
try whether it
So
works again.
yeah.
Yeah, it works now. Yeah.
Yeah. So yeah, it's back on. Yeah. Yeah, great. Yeah, so before I close the session, I would like to do some marketing and promotion. Yeah, so together with the publisher, we're actually organizing an international conference on the future of additive manufacturing next year in Singapore at our iconic Marina Bay Sands in August, just before our National Day. So the theme for this conference will be additive manufacturing powered by artificial intelligence. So so we look forward to welcome you all to Singapore. We are still in the midst of preparing the website. So once the website is launched, well, we'll reach out to all of you again. Meanwhile, feel free to contact us if you have any questions regarding this conference. Yeah. Yeah, so I also like to promote our new journals with this X Science publisher as well, Engineering Science and Additive Manufacturing. So it aims to be a complementary journals to material science, where we look more into the process and the engineering fundamentals behind additive manufacturing, and it's currently open for submission. So I look forward to your support for this journal as well. And yeah, finally, thank you for everyone for attending today's seminar. To find out more about material science and additive manufacturing, feel free to scan the QR code at the slides to connect with us as well. Yeah. And finally, or if you have any interest to discuss research topics or on the journals and conference, feel free to connect with me. I have provided two QR code. On the left is QR code for my email and my LinkedIn profile. And on the right is WeChat for the audience that are using WeChat. Feel free to connect with me as well. Yeah. So with that, I would like to close today's webinar. So again, thank you very much for attending, and once again, thank you to the two speakers for the very interesting and enriching talk. Yeah, thank you very much. Yeah, and have a good
Thank you,
day.
Professor Singh. Thank you for the audience.
Yeah.
If everyone have an interest of submission, please contact Wendy and contact our office. I just have the emails here. So yeah, thank you, Professor Singh, and thank you to speakers. It's a wonderful webinar. Yeah.
Yeah, thank you so much.
Okay, I think we can just quit and have a good day. Yeah.
Thank you. Bye.
Bye, Dr. Meter. Yeah. Oh, thank you, Professor. That's very interesting, and welcome every editorial board member to join this webinar. We would like to share more interesting topics in the future webinar. So yeah, if you would like to share, please contact Wendy. I think it's also our pleasure to have more editorial board member to share their topics, to share their like insights. Yeah. Well, we will end this meeting now. So thank you. Bye. Have a good day.